Okay, welcome again to this lecture series. In the previous lecture, we have discussed about the continuous time, complex exponentials and sinusoidal functions. And we have seen that these two signals, e raised to power j omega t or a cos omega t plus phi, these signals has two major properties. First was that they are always periodic with a time period of 2 pi by omega, and these signals in the continuous domain, they have infinite and bandwidth. That is, for different values of frequencies you always get different signals, and as you increase the frequency, the rate of oscillation increases. Okay, now we will discuss about the discrete case. Okay, so discrete time complex exponentials are sinusoids. Again, like the continuous time case, the complex exponential and the sinusoidal signals in discrete time, they have the similar properties. Okay, so we start with a discrete time complex exponential, which is in the form of e raised to power j omega n. Okay, where n is a integer. Or when you define a sinusoidal signal in discrete domain, you can write as omega n plus phi. So you are using a different notation here, omega. In the previous case, we have used capital omega for continuous time. We are using this omega for discrete time, just to differentiate. Okay, now these signals are different in some aspects as compared to their continuous counterparts. So we will explore the properties of these. The first property of this signal is that this is a signal with a frequency of omega. Okay, now omega here is different. Omega here is in radians per sample. Okay, here as well as here. In the previous case, this omega, it was number of radians per cycle, and you can also write this omega in terms of f, that is become 2 pi f. Again, we have used a different notation there. Omega is equal to 2 pi capital F. So capital F is the continuous time frequency, and this omega is equal to 2 pi f, where small f is for the discrete time signals. This is a differentiation between the two. Okay, and f, the units of f will be now, capital F was number of cycles per second. This will be number of cycles per sample. Okay, so this is the difference in the frequencies between the continuous and the discrete time case. Okay, what do you mean by number of cycles per sample is, suppose if I take a periodic discrete signal like this, suppose this is okay, this is a discrete time signal, sinusoidal signal, a plotted a cos wave form in discrete domain. This is a cos function. Okay, now this is one cycle. Okay, let us suppose you have 12 samples in one cycle. Okay, in one period, in one time period, you have 12 samples. So what will be the frequency? It will be nothing but 1 by 12. Okay, or you can say that the time period of this is basically 12 because it repeats after 12 samples. So number of samples in one cycle is 12. So what will be the number of cycles in one sample? That is nothing but 1 by 12. This is what is the frequency in discrete case. Okay. Now to see the difference between the analog and the continuous and the discrete time signals, the first difference you will see that if I take a signal, this signal has a frequency of omega. If I take another signal with a frequency of omega plus 2 pi n, okay, so this signal and this signal, what is the difference between them? There is a difference of frequency. This has a frequency of omega, this has a frequency of omega plus 2 pi. It means the difference in their frequencies is 2 pi. And if you see this signal, it will become e raised to power j omega n multiplied with e raised to power j 2 pi n. And e raised to power j 2 pi n, where n is a integer, it is nothing but 1. It is cos 2 pi n plus j sin 2 pi n. So cos 2 pi n is 0, sin 2 pi n is, cos 2 pi n is 1, sin 2 pi n is 0. This is cos of 2 pi n plus j sine of 2 pi n. So this is always equal to 1. So this again becomes e raised to power j omega n. Okay. So what it means, it gives you a very important property now there, that two signals, discrete time complex exponential signals with a frequency of omega naught, suppose, and omega naught plus 2 pi, they are identical. Okay. Whereas this was not the case with continuous time. You have different signals for different frequencies. This is not the case here. Within a band of 2 pi, the signals will be different, but if you go beyond a band of 2 pi, the signal will start repeating. Okay. So in discrete time signals, we concentrate on a frequency band of 2 pi. So within that 2 pi, all the signals will be unique. Beyond that, the signal just starts repeating. Okay. So like in the continuous time case, the frequency range can vary from minus to plus infinity. In this case, the frequency range is finite. Okay. So your frequency can take only a band of 2 pi. So it can be maybe from 0 to 2 pi. Generally we take this. Or it can be from minus pi to pi. This is called as fundamental frequency range. Okay. So within a band of 2 pi, the signals, they are different. If you go beyond 2 pi, the signals, they will start repeating itself. So if you have a sinusoid with a frequency of, if you have a complex exponential or sinusoid with a frequency of omega naught, okay, and you take another sinusoid or complex exponential with a frequency of omega naught plus 2 pi, these will be the similar signals. And same you can say in the sinusoidal signals, you have omega n plus phi. Okay, this has a frequency of, the frequency of this signal is omega. If I take another signal where there is a difference of 2 pi in the frequencies, cos omega plus 2 pi and plus phi, okay, and if you solve this equation, you will get omega n plus 2 pi and plus phi. So I can write it as a cos of 2 pi n plus omega n plus phi. Okay, and this is nothing but cos of 2 pi if I write it as x. So cos of 2 pi n plus x is nothing but cos x. So it again becomes a cos of omega n plus phi. It means again this signal and this signal, they are same. Okay, so those signals which are separated in frequency by 2 pi in discrete time, they are same. So this is what is an important property. Okay, so discrete time complex exponentials and sinusoids which are separated by a frequency of 2 pi are similar. This is the important difference between continuous time and discrete time. So in the continuous time we had this equation minus infinity to omega less than infinity. In discrete time we have minus pi to pi. Okay, so the signals which has a frequency between minus pi to pi, if you go any signal beyond this frequency you will get a similar signal in this band. Okay, what it means is that suppose you have some sinusoid function which has a frequency lying between minus pi to pi. If you take another sinusoid, this is the fundamental frequency band. Okay, all the discrete time signal frequencies, they will come under this band. Beyond this, if you go beyond this band, you will get a similar signal within this band. It means if I take a frequency here, okay, now you will get a signal within this band which is very similar to this frequency. Okay, so between minus pi to pi or pi to, if you take 3 pi, they are same. Between 3 pi to 5 pi, again a band of 2 pi, you are getting the same frequencies. So in discrete signals we just concentrate on a band of 2 pi. Okay, so this is very important thing. We concentrate only on this frequency band between minus pi to pi, because beyond this frequency band, if you take any frequency you will get a similar frequency within this band. So your discussion in the frequency domain is limited to 2 pi only. Okay, so it is not only 2 pi. You can say that if you write equation omega k is equal to omega naught plus 2 pi k, where k is 0, 1, 2. So omega naught is between minus pi to pi. If omega naught is between this band, any other frequency defined by this equation, omega naught plus 2 pi k, means the difference in the omega naught and omega k is a multiple of 2 pi. It may be 2 pi, it may be 4 pi, it may be 6 pi, they are always same. So that is why we say that all these frequencies omega k which are separated by omega naught with a multiple of 2 pi, they are called as the Alice frequencies, because you will get a similar frequency like this within this band. Okay, so you do not have to go beyond this band. And when we see sampling theorem, this is a very important concept there. When you have a continuous time signal, you have an infinite frequency range. Okay, but when you convert this signal, you have a continuous time signal, it can be any frequency. But when you convert this into a discrete time signal using a sampling process, you have a finite frequency range, that is minus pi to pi. So you have to make sure this sampling is nothing but basically mapping of the frequencies from continuous domain to discrete domain, and you have to make sure that this mapping must be unique. Okay, it means the infinite range of frequencies in the continuous time must only be mapped within this band of 2 pi, otherwise you will get a nice frequency. There will be a problem in reconstructing the continuous signal from its samples. Okay, that we will see in more detail. This is the first property. The first difference between continuous time and discrete time, complex exponentials and sinusoids. So continuous time signals, they have infinite bandwidth, and discrete time signals have a finite frequency band of 2 pi. Okay, so in fact any frequency, so minus pi to pi, it means omega should be limited. This any omega where the magnitude of omega is greater than pi, you will get a identical frequency which is will be available in this band. So you have not to go beyond this band of frequencies from minus pi to pi, otherwise you will get Alice frequencies. Alice frequencies means a similar frequency will exist in this band. This is not only minus pi to pi band, you can choose any 2 pi band. It may be 0 to 2 pi. Okay, it may be 0 to 2 pi band, it may be 2 pi to 4 pi band, and so on. But once you choose a band of 2 pi, the signals, they are unique, and if you go beyond that 2 pi band, the signal will start repeating. Okay, so generally we consider minus pi to pi because we have positive frequencies as well as negative frequencies which are necessary to generate a real signal. Okay, so this is the first property. Now the second important difference between the continuous and discrete time signals. When we have discussed the continuous time signals, we have said that they are always periodic. Okay, so x of t is equal to a raised for j omega naught t, or x of t is equal to a cos omega t plus phi is periodic with a time period of 2 pi by omega, always periodic. This is not the case here. Okay, if you say xn is equal to a raised for j omega n, and you want to see whether this should be periodic or not, let us suppose it is periodic with a time period of n. Let the time period for this signal be n. Okay, if it is periodic with n, what it means is that again x of n plus capital N should be equal to x of n. So the signal will repeat after n samples. Now see, the time period in this case, it can be only integer value, it cannot be fractional because we have sampled at 0, at 1, at 2, at 3. Okay, the time period should also be integer. It cannot repeat after 1.5 or 2.5. It has to repeat after 1 sample or 2 sample or 3 and so on. Okay, now if you use this equation here, you will get e raised power j in place of omega. In place of n, I write n plus n. This should be equal to e raised power j omega n for periodicity, or e raised power j omega n into e raised power j omega capital N must be equal to e raised power j omega n. So again this factor must be equal to 1. Then only this equation will hold and it will be periodic with a period of n. And e raised power j omega n is equal to 1. What it implies that your omega n must be a multiple of 2 pi. Okay, because e raised power j 2 pi k is 1. It may be 2 pi, it may be 4 pi, it may be 6 pi and so on. So what you can say from this equation is that omega upon 2 pi should be equal to k by n. This is another major difference. Okay, it means if this signal is periodic with time period n, then its frequency omega naught by 2 pi, it should be the ratio of two integers, k and n both are integers. If it is not the ratio of two integers, this signal is not periodic anyway. And how you get the time period? You first find the frequency using, you can also write this as f, because omega is equal to 2 pi f. So f is omega by 2 pi. So you first express, or you find the frequency of this complex exponential signal. If it can be expressed as a ratio of two integers, if there are some common factors, you have to cancel them out so that k and n becomes prime, and the denominator of this will give you the time period. Okay, and the same concept will hold for this signal. Xn is equal to a cos omega n plus phi. Again, this will be periodic if and only if its frequency will be the ratio of two integers. If the frequency is not the ratio of two integers, it is not going to be a periodic signal. So discrete time signals, they may be periodic, they may not be periodic, depending upon whether the frequency is the ratio of two integers or not. Okay, let us take an example. Suppose I take two signals, one in the continuous time, xt is equal to e raised to power j, maybe pi by 2t, and xt is equal to e raised to power j pi by 2n, e raised to power j pi by 2n. Okay, now t here is continuous, okay, and here is discrete. This is the difference between time continuous and discrete time signals. Now this is periodic, and what is the time period? 2 pi by omega. And what is omega here? Omega is pi by 2. So you get 2 pi divided by pi by 2. So you get it as, and this will become 2 pi into 2 by pi. You will get time period as 4. Okay. Now what about this? You have to first check its frequency f, that is omega by 2 pi, whether it can be expressed as the ratio of two integers or not. If it is can be expressed as the ratio of two integers, then only this is periodic. So what is omega here? It is again pi by 2. Okay, so what will be omega by 2 pi? It will be pi by 2 upon 2 pi. So it will be pi by 2 into 1 by 2 pi. You will get 1 by 4. Okay, now f, I have expressed f, which was omega by 2 pi. It is 1 by 4, which is expressed as the ratio of two integers, that is in the form of k by n. So what is the time period? N, that is denominator. So time period for this is nothing but 4. So both the signals, they repeat, this repeat after 4 seconds, this repeat after 4 samples. Okay, now you take another example. Suppose I take xt is equal to e raised to power j 2t. Now what is time period? 2 pi by 2. This is pi. And if you take xn is equal to e raised to power j 2n, what will be f omega by 2 pi? You will get omega in this case is 2. So 2 upon 2 pi, you will get 1 by pi. Now it is not in the form of the ratio of two integers. So this is basically not a periodic signal. Okay, in continuous time it is periodic, no doubt, but in discrete time this is not periodic because the frequency is not the ratio of two integers. You are getting pi, which is a rational number now here. Okay, so to check whether a discrete time signal is periodic or not, you have to see its frequency. If it can be expressed as the ratio of two integers, then only it can be periodic, otherwise not. Okay, let me take one more example. Xn is equal to, suppose 2 cos of pi by 4 and plus pi by 2. You have to find the time period for this signal. So first you have to see what its frequency. It is pi by 4. This is phase, this is amplitude. Okay, and then you have to compute its frequency omega upon 2 pi. So it is pi by 4 divided by 2 pi. It is pi by 4 into 1 by 2 pi. You get 1 by 8. So you can express this in the form of k by n, and n will become the time period. So time period for this is 8. So this signal will repeat after 8 samples. Okay, now so this is what is the difference between the continuous time and discrete time signals. So there are two major differences that we have got. Okay, and one more thing that I need to discuss here is that in case of discrete signals, we have seen, in continuous signals we have seen that as you increase the frequency, the oscillations they start increasing. Okay, and the frequency can go up to infinity. Now in this case, cos omega n plus phi, this is not the case, because the frequencies they are limited to a band of 2 pi only, within a band of 2 pi. It means if you go beyond 2 pi, the signal will start repeating. Okay, so omega, if you start from omega is equal to 0, you get a constant signal. Then as you increase omega, when omega becomes equal to pi, you will get the maximum rate of oscillation. Okay, see, I will explain this. We have a signal a cos of omega n plus theta. Okay, if you plot this for different frequencies, maybe, or I take omega naught in specific, if you take omega naught is equal to 0, then increase the frequency maybe pi by 8, and then pi by 4, pi by 2, and so on up to pi. How the signal will look like. Or to make it more simple, just take cos of omega naught, and I am omitting the phase here. So when your omega naught is 0, you are getting a constant signal. Cos 0 is 1. Okay, so cos of a cos omega naught n for omega naught is equal to 0, you are getting a signal like this. Okay, at each instant of n, this is equal to a. Or if you just take cos omega naught n, it is 1. Okay, then I increase the frequency. We go from DC frequency to higher frequencies. We suppose we have a frequency of pi by 8. Okay, so how this signal will look like? We have cos of now pi by 8 n. Omega is pi by 8. When you plot this signal at 0, you are getting 1 because cos 0 is 1. Then at n is equal to 1, you will get cos of pi by 8. Then cos 2 pi by 8, that is cos of pi by 4, and so on. When n will become 4, you will get cos of pi by 2, that is become 0. So 0, 1, 2, 3, and 4. It means at n is equal to 4, you are getting a 0 crossing point. Then as you increase n, you are getting the negative values. Okay, when n becomes 8, this is at n is equal to 4. When n becomes 8, you will get cos of pi. It becomes maximum. In the negative direction, that becomes -1, and then it will again start decreasing. So we are getting basically 4 non-zero samples, then a 0, then again 4 non-zero samples, And so this is one time period. This is one complete cycle now. Okay, so 8, this is 12, this will be 16. So after 16 samples, the signal will repeat. Okay, and if you compute its time period, you can see that omega is pi by 8. So omega by your f, which is omega by 2 pi, it will be pi by 8 upon 2 pi. You will get 1 by 16. Okay, so ratio of two integers, and denominator is your time period n. Okay, now if you further increase the frequency from pi by 8 to suppose pi by 4, so pi by 4, in that case what will happen, this will become pi by 4, your time period will become 8. Okay, so the rate of oscillation is now increasing. As you're increasing the frequency, the rate of oscillation cos of pi by 4n. So you will get, now in this case, when you will get 0, when n is equal to 2, because cos, it will become cos of pi by 2 for n is equal to 2. So at 0 you are getting a 1, then at n is equal to 1, you are getting non-zero value, at n is equal to 2 you are getting a 0. Then in the negative direction, so you are getting two non-zero samples, then 0, then again when it will become 4, 0, 1, 2, 3, 4, it will become maximum, then 5, then at 6, cos 3 pi by 2, it will again become 0. Okay, so you're getting basically 3 non-zero samples, then again, and so on. Okay, so this will become 0, 1, 2, 3, 4, 5, 6, 7, 8. So after 8 samples, this signal will start repeating itself. Okay, so you have higher frequency now, means you have more oscillations now. This is a low frequency, this is a more high frequency. Similarly for pi by 2, when you take pi by 2, what you will get, cos of pi by 2n. So for n is equal to 0, you will get 1. For n is equal to 1, you will get 0. Then for n is equal to 2, you will get cos pi, that is minus 1. This is minus 1. Then for n is equal to 2, sorry, for 0 you are getting 1, for 1 you are getting 0, for 2 you are getting minus 1, for 3 you are getting again 1, cos 3 pi by 2, then 0, then minus 1, then 0, 1, and so on. Now see, the signal fluctuates more. First you are getting 0 after 4 samples, then you are getting 0 after say 3 samples. Okay, then you are getting 0 just after 1 sample, or sorry, 2 samples. Okay, so 1, then 0, 1, 1, 0, minus 1, then again it will be 0 here, then 1, 0, minus 1, 0, 1, then 0, then minus 1, and so on. Okay, so as you increase the frequency, the rate of oscillation is increasing, and you will get the maximum rate of oscillation when the frequency becomes equal to pi. Okay, because when you plot cos of pi n and lay cos of pi n, so at n is equal to 0, you are getting 1, at n is equal to 1, cos of pi minus 1. Okay, then 1, then minus 1, then 1, then minus 1, 1, minus 1, and so on. So this is the maximum rate of oscillations that you can have in a discrete signals when the frequency is equal to pi. So the signal fluctuates simply between 1 and minus 1, 1 and minus 1. So there are two high rapid oscillations. This is the highest frequency signal. Now what happens if you go beyond pi? Okay, the signal, so you have a frequency axis like this. We have started from 0, constant signal. As you increase the frequency, the rate of oscillation starts increasing, and then when the frequency is equal to pi, you are getting the maximum oscillations in this signal. And beyond this, what will happen if you go for frequencies between pi to 2 pi? They will be same as the frequencies between pi and 0. Okay, because when you further increase the frequency, the rate of oscillation will start decreasing. Okay, and when it will reach as 2 pi, it will become cos 2 pi is 0, again this signal. Okay, it means you are going like this. So 0, then we are getting high frequency, then this frequency, then this frequency, then this frequency, then this signal up to pi. Now beyond pi, when you go from pi to 2 pi, this signal will repeat like this. Okay, it will go from this frequency, the lowest frequency, then lower than this, then lower than this, and finally will reach at this signal. Okay, it means if you take one signal with a frequency of cos omega 1n, where omega is between 0 to pi, and you take another signal with a frequency of omega 2n, where omega 2n is nothing but 2 pi minus omega 1. Okay, so any frequency beyond this, if I take this as the frequency, this can be taken as, this is the total 2 pi minus this much, which is nothing but this frequency band. Okay, so this frequency, you will see it will be similar, cos of omega 2. Omega 2 is nothing but 2 pi minus omega 1 n, and that will simply become cos of omega 1 n. Okay, it means as you increase the frequency from 0, your rate of oscillation starts increasing till you reach pi. At pi you have the maximum frequency, then as you increase further the frequency, it starts decreasing. At 2 pi it is same as 0. Okay, so we have to limit our frequency band between this pi. It means any frequency for which mod of omega is greater than pi, you will get a similar frequency within this band minus pi to pi. So those will be the aliases of this frequency band. Okay, so these are three important properties of discrete and complex exponential signals that we have discussed. So I will just conclude what we have discussed here. For continuous time case, we have defined a signal like this: xt is equal to e raised to power j omega t or xt is equal to a cos of omega t plus phi. You can also introduce here, I have not used it, but you can also write this as a cos omega t plus phi. This hardly makes any difference. You will get the same property. And in the discrete case, you have xn is equal to e raised to power j omega n, and sinusoidal equivalent is a cos of omega n plus phi. Okay, so what are the differences between these two signals? They are always periodic. They are always periodic with a time period of 2 pi by omega. These two signals, they may or may not be periodic. That depends upon their frequency, which is omega by 2 pi. If it can be expressed as the ratio of two integers k by n, then only it is periodic, and this n gives you the time period. Okay, but you have to make sure that you have to factorize any common factors. Like suppose if I take one case, if you have omega by 2 pi is equal to 30 by 60, so you cannot say 60 is the time period because it becomes 1 by 2. Okay, after factor, so 2 is the time period. And if you take 31 by 60, in this case 60 is your time period. Okay, and one more difference you can see that 30 by 60 and 31 by 60, if you see as a number there is no too much difference, but you can see a large difference in their time periods. One has a time period of 2, another has a time period of 60 samples. A small difference in the frequency can cause a large difference in the time periods in discrete signals. This is one difference. The second difference that we have studied, that these signals they have the infinite bandwidth. Okay, and these signals, their frequency is limited to a band of 2 pi only. So minus pi to pi. This is the fundamental frequency range. All the discrete time sinusoids will have frequency within this band only. Okay, any frequency which is beyond this band, that will be Alice frequency. It means you will get a similar signal like that within this band. So this band constitutes all the frequencies of discrete time sinusoids. Okay, and the third one is that as the frequency increases, the rate of oscillation increases, but in this case this is not the case. So as you increase the frequency omega naught from 0 to pi, the rate of oscillation starts increasing till you get pi. At pi you are getting the maximum oscillations or maximum frequencies. Okay, and if you go beyond pi, the frequency again, the frequency starts increasing, but the rate of oscillation starts decreasing till you get 2 pi, which is again equal to omega is equal to 0. Okay, so you can say in this case that the high frequency signals, the frequencies which are close to minus pi or pi, they are the high frequencies. Okay, and the frequencies which are close to 0 or 2 pi, they are the low frequency signals. Okay, or in general you can say the frequencies which are close to the odd multiples of pi, they are high frequencies. Okay, the frequencies which are close to the even multiples of pi, they are the low frequency signals. Okay, so next we will discuss and another important concept, why these signals are important. Okay, why we basically study the complex exponentials or sinusoidal signals, because they are the basis. Okay, I have already told you that they are the building blocks, and how they act as building blocks, that we will discuss in the next lecture. Thank you.